Hi, my name is Carlos Hervias. I'm a postdoc at the Pontificia Universidad Católica de Chile, and I'm going to present my work on modeling parity-violating spectra in galactic dust polarization. So the motivation for this entire work is thermal dust, which has a positive parity-violating TB spectrum as measured by Planck. You can see here a couple of examples of that power spectra measured from the 353 gigahertz channel. Also, the EB spectrum is still consistent with zero within the Planck sensitivity. So if EB is different from zero in dust, how does this affect cosmic birefringence? This is the main motivation for this work. So filaments is one of the features that we can see in thermal dust. It has been observed in the millimeter in Planck data, for example, as you can see here in this coad of the intensity and polarization for this filamentary structure, as well as other frequencies. So here, for example, in the left, you can see infrared images with Herschel. And when you take the derivative of this image, you can see the filamentary structure. This filament as well as correlated with the H1 21 centimeter line, as can be shown here. Filaments have been put forward as a mechanism that can explain this parity-violating emission. So the key is the misalignment angle between the underlying galactic magnetic field and the long axis of a filament. So here, for example, you can see here this red object as a filament, which has some long axis. And then in blue, you can see the magnetic field, and this is in 3D. And then if you project it into the plane of the sky, you can see that the angle formed between these two is this psi angle, this misalignment angle. So an asymmetry in the handedness of this angle can generate non-zero TB or non-zero EB spectra. So this asymmetry basically means that you have a higher fraction of filaments with a positive angle than a negative angle, for example. So using this idea, we can, a few works have explored this idea of estimating this misalignment angle psi using the cross correlation of the 21 centimeter line of H1 with the data from Planck. So, for example, here you can see a couple of examples of this angle being estimated, and we can in real data, and we can see it has like a couple of like a few the value of a few degrees in this multiple range between 100 and 600 or so. So on the other hand, we have cosmic birefringence. So all measurements from all these recent measurements from Planck and from WMAP data account for this dust EB intrinsic emission being different from non-zero. So the most precise measurement to date from Eskil and Komatsu 2022, they use this filament magnetic misalignment ansatz, in which this psi angle is measured from the TB and TE spectra. So the idea is that the EB from dust is measured is proportional to the EE spectra of dust, and this term that includes this misalignment angle, and this misalignment angle is basically measured from a ratio between the TB and the TE spectra measured directly from dust, from the 353 gigahertz channel from Planck. So this model of misalignment angle works even if it's relatively simple. Then another idea we can use to account for this is to use a dust template to directly measure this EB emission from dust. So, for example, here we have two plots from papers by Patricia Diego Palazuelos that show this effect of measuring the cosmic birefringence angle as a function of the different sky fraction. And here we can see the effect of dust through including more or less sky, and how this affects this estimation of this cosmic birefringence angle. So clearly more work is needed to try to understand what is the impact of dust on cosmic birefringence. So the filament model in this work was published in this paper in 2022. So we basically create GKU realizations of filamentary dust. And the idea of this work was to be able to reproduce like the features we see in Planck dust. So for example, the BB to EE ratio being 0.5, and the TE correlation, and the power loss spectra, etc. So the advantages of this model is that we can create realizations with different seeds. We can create non-Gaussian features from the filament at small scales. We can also introduce some arbitrary amount of frequency decorrelation. And for example, we have used this filament model in this paper, Abril Cabezas et al. 2024, where we studied the non-Gaussianities, the effect of non-Gaussianities on the covariance for estimating the tensor-to-scalar ratio in forecasts. So the basic idea is that the orientation of the filaments in this model can be manipulated. So we can basically take a filament and then manipulate this misalignment angle such that this angle follows some arbitrary probability distribution function that has some asymmetry until it basically looks like this sky observation. So here, for example, you can see a test where we or in this paper we use this asymmetric Laplace distribution, which is one example of a probability distribution function that can create asymmetry, having more positive values than negative values. And we also test a normal distribution, which we offset slightly to a positive value, such that you can create an asymmetry. So how do we estimate this angle, this misalignment angle? We follow the estimators shown in Zuckerman et al. 2023. So first, we need an estimation of the filament orientations. So for that we use the 21 centimeter line from H1 data. So here you can see an example of this Hessian method, Hessian matrix method, in which you have a map of the intensity from the 21 centimeter line at a given velocity. And then you calculate the Hessian matrix, which is basically the second derivative, and that gives you the edges of these filaments. And then from that you can figure out the orientation of the magnetic field, and from there you can construct a polarization map. Like you can construct like a Q and U map just from the intensity of the 21 centimeter line, and then you do this at different velocities, meaning different values along the line of sight, and then you basically integrate along the line of sight. The Rolling-Hoff transform is an alternative to this method that works on a similar idea. So once you have this template of TQU maps derived with H1, you can estimate this misalignment angle. So you can do a map-based estimator in which you sum over pixels. So for example, you can derive a map like this, showing you this misalignment angle for different directions in the sky. And then you can also define some spectra-based estimators in which basically you just calculate ratios between spectra, and these spectra are cross correlation between this H1 derived template and the dust observations directly. So in our filament model, we don't really have H1 observations, but we do have another way of measuring this along the line of sight, which is basically having the intensity of this filament model at different concentric shells at different radii along the line of sight. So here we can see an example of that, where you have 20 different concentric shells here in color. And then you can derive a Q map and a U map here in the middle and the bottom. And then you can integrate along those 20 radial shells, and then you can construct this map, for example, and then you compare that with the Q map derived from the filament model directly from the dust simulation. And if you compare these two, you can clearly see the correlation. And the same for you. So the basic idea of this is that just from the intensity at different radial shells, you can derive this polarization template, this Q and this U template. So we fit these estimators. We calculate these estimators we calculate them with the data, with the real data shown here as circles, and then we calculate these same estimators on our on our filament model for different realizations of the filament model. And then we find the combination that maximizes the likelihood, that maximizes the posterior probability. So here, for example, you can see the example using this asymmetric Laplace distribution and using the Hessian method to estimate this GKU template. So we have two parameters. One parameter that controls the asymmetry of the filament population. So how much have a positive misalignment angle versus negative. And here we have a parameter that controls the scales, or basically the width of this asymmetric Laplace distribution. And then we just calculate these estimators for different combinations. And then here you can see, for example, the values that that best fit the observations. So with this, we define a fiducial filament model using the asymmetric Laplace distribution with a kappa parameter, which is this parameter that controls the asymmetry of 0.003, and a lambda parameter, which is the one that controls the width of the distribution of 0.14 inverse degrees. So this asymmetry here corresponds to having 56% of the filaments with a positive angle and 44% of the filaments with a negative angle. And then here on the left, we can see the power spectra calculated on this Planck galactic plane 70% mask. So the dashed lines is the fit to the M pipe data. And then the circles is the power spectra calculated from our filament model. So from top to bottom here is TE, EE, BB, TB, and EB. And of course, they match here by construction because that's how we define our filament model. But also you can see that the TB spectrum produced by our filament model is a good fit to the Planck model, to the Planck fit, to the Planck power law fit. And then here in green, you can see that our model produces a few microkelvin square of EB power spectra. So what is the application to cosmic birefringence? So we can use the realization of our model in cosmic birefringence pipeline. So we apply this to the Minami-Komatsu method. So we can use like I mentioned before, like we can estimate the filament ansatz directly, or we can estimate it directly from a template. So then in this observed EB power spectra, we want to account for this term here, which has the intrinsic EB emission from foregrounds or from dust. So in this paper, we show results for using this 70% galactic plane mask and using N-pipe frequency maps within the HFI channel, so 100, 143 to 17, and 353 gigahertz, and the A and B detector splits. So this is the first example using the method in Eskil and Komatsu 2022 that uses the filament ansatz. So here on the right, we can see in red the misalignment angle estimated from the 353 gigahertz N-pipe maps. And then in blue, we can see the estimate from 100 realizations of our filament model. And then we run the pipeline to estimate the cosmic birefringence angle. And you can see here the posterior on the cosmic birefringence angle from both of estimating this misalignment angle from both of these sources. And you can see that our measurement of beta is consistent within 0.8 sigma from using the M-pipe 353 map. And this is a second attempt using the method in Diego Palazuelos et al. 2022, where a model or a template is directly used to estimate the EB spectra. So here on the left, you can see the Commander Sky model being used as a template. So calculating the EB spectrum in red, and then in blue you can see the mean of 100 realizations of our filament model. And then here on the left, you can see the same idea of this running the pipeline and then comparing the posterior probabilities for beta using both cases. And in this case, the measured beta is consistent within 0.4 sigma. So conclusions, the main result from this paper is that we present a model of dust that has intrinsic non-zero TB or an EB spectra. We calibrate our model to sky observations. And our model, with our model, you can generate multiple realizations with multiple seeds. And you get this intrinsic parity-violating emission on top of all the other effects that can be studied with a filament model, like the non-Gaussian features and the frequency correlation, etc. So in August, we put a paper on arXiv. So you can see here the number if you have a look. The main application of this model is to be used as dust in simulated observations for forecasting. So you can make simulated observations, and then you can use as your dust this model with non-zero EB emission. And the idea is that we can try to forecast and try to measure the impact on isotropic or anisotropic cosmic birefringence measurements. So we are working on this right now, and hopefully in the next few months we can have a paper out trying to forecast this. And also this model can be used in the analysis of real data and observations as was exemplified here. So as you can see, so far our results show that the impact on measuring the cosmic birefringence angle is minimal. And that's it. Thank you so much.